students. Today's session we will see different types of stresses induced in machine components and how to design the components which are subjected to eccentric load. Objective of today's session: understand the different types of stresses induced in machine component and describe eccentric axial loading. That means after this session you will be able to understand the different types of stresses and you will able to describe eccentric axial loading. Let us say different stresses induced in component. The before that, when any machine component is subjected to load or a force, maybe in tensile or the in compressive load or a tensile load, that time internal resisting force gets induced in it to resist that force which is acting on it. This internal resisting force per unit cross sectional area where which this internal resisting force acts to oppose the load are known as the stresses. That means stress means the ratio of internal resisting force per unit cross sectional area. Now here when machine component you will find in mechanical system many machine components are subjected to different type of stresses, and to design such the elements or the components of the subsystem or a system, we have to find out the different stresses induced in it to design to find out their size and dimensions. Now here stress is classified into here three types. Now here first one is the direct stress or simple stress. Direct means when the component is subjected to the forces which are acting along this axis here, or directly it may be the tensile force or a compressive force. Direct stresses gets induced in it are also known as the simple stresses, and these are further classified into two types: shear stress and normal stress. Further, normal stress which are perpendicular to that plane, that is tensile stress or compressive stress. And another type is shear stress. That means direct stress classified into two: shear stress, normal stress, and normal stress into tensile stress and compressive stress. After that, second classification here, torsional stress. Sometimes some elements such as shaft subjected to twisting moment, the torsion stresses are going to induce in it. Then bending stress, because of the load, bending of the elements or components may take place, bending stresses are going to induce in it. Now another classification, that is of indirect stresses, that is torsional stress and bending stress. And third one is the combined stress. Combined means combination of torsional as well as bending as well as the axial, or maybe combination of torsional or bending. And you will find in shaft is subjected to combined stresses, bending as well as the torsional. And if the components such as helical gear which is mounted on the shaft, and because of that you will find the axial component which is acts due to the helix of the helical gear on the shaft. Now let us see different stresses. The first one here you will find, this is the machine element or a member when it is subjected to tensile force. We look at this diagram. You will find because of this the tensile stresses gets induced in it. These are the internal resisting forces. Therefore, you will get here the sigma T is tensile stress is equal to P upon area. P means this internal resisting force upon area. But to make the analysis simple one, we are assuming the intensity of this internal resisting forces which is equal to the load which is acting on the component, that is P. That's why sigma T is equal to P upon area. And this cross sectional area we are going to consider it depends on the cross section of the element. This is about sigma T, that is tensile stress. Another direct stress is this shear stress. Look at this, the rivet when it is subject, two plates are joined by using the rivets. When it is subjected to the force P, because of that you will find at the middle the shear of the rivet may occur. There may be possibility of shear failure of the rivet, and in this case when because of this shear stresses gets induced in it, the when external force acting on the component tends to slide here the adjacent plane with each other because of this force P and this force P. There may be sliding, and because of that stresses are going to induce in the component, and these stresses are known as direct shear stresses, and these stresses are calculated tau is equal to P upon area. Try to understand. Then next one, look at this, the simple stress again. Now in this machine member, it is subjected to tensile forces acting outward direction. But when the component, look at the another case, when component which is subjected to the axial forces or the load, but they are compressive, that means acting towards each other. Look at this, and because of that, what is happening? The dimension of the component is going to increase, but internal resisting stresses are going to induce it, and these stresses are compressive stresses. Because of this force is also compressive, the sigma c is equal to P upon area. Again, cross sectional area we are going to consider here, therefore sigma c is equal to P by. That means direction of the forces, whether it's compressive or the tensile, which decides sigma t and sigma c. And here is the shear stress. That means this tensile stress, then the compressive stress, then the shear stress, all these are the direct stresses or simple stresses. Again, you will find in case of direct stress or the simple stresses, the elastic limit E plays important role. E is equal to sigma upon epsilon. That means within the elastic limit, stress is directly proportional to strain. Change in dimension upon original dimension is the strain. Now again, in this case, in shear, what is happening here, you will find there is, because of this shear stresses, it is going to change the or distortion in original, the right angle is going to occur because of the shear stresses. And because of that, the another term, that is capital G, is known as constant of proportionality or modulus of rigidity, which plays important role in case of shear stresses. E is the modulus of elasticity, mu is the Poisson's ratio. And again, you know very well the relationship between this modulus of elasticity, modulus of rigidity, and Poisson's ratio is given by E is equal to 2G in bracket 1 plus mu. And again, for carbon steel, the value of G is 80,000 Newton per mm square. For cast iron, the value of G, that is 40,000 Newton per mm square. And for mu, Poisson's ratio for carbon steel, that is 0.29, and for cast iron is 0.21 respectively. Again, how to find out the permissible shear stress? Tau permissible is equal to SSY upon FOS, and generally you will find again 0.5 SYT upon FOS also. This is about the direct stresses induced in the component tensile, compressive, and shear stress. Now let us see the another one, indirect stresses. The stresses induced, indirect stresses induce the component, that is stresses due to bending moment. Now when, look at this is one of the beam when subjected to bending moment MB, which is shown here. Because of that, what is happening, you will find here at this axis or at this section, you will find because of the force, the inside, the surface of the beam, which is going to subject the compressive stresses from this neutral axis, and this portion, half portion, which is subjected to tension. Even though you can do it at home by taking one wire in your hand, you can bend it, you will find outer, the external outer surface which is subjected to tensile, and inside surface of the wire which is going to subject to the compressive stresses, which is shown here because of this bending. And how to find out this bending? Now here the cross section which is shown, maybe square, maybe rectangular, maybe circular. Accordingly, we are going to find out its mass moment of inertia I. How to find out the bending stress at any fiber at a distance from this, at the any section that we have to find out. So we can easily find out sigma B is equal to, by using simple equation, MBY by I, where MB is the bending moment, Y is the distance here from the neutral axis to the outermost fiber. Again, you will find this, the bending stress is maximum in the fiber which is farthest from the neutral axis. Try to understand. Therefore, stress distribution of stresses, which is linear, which is shown here, the compression and here tensile, depends on the the bending of the components. Again here we can easily find out the magnitude of this bending stress sigma b by using this equation mby by I. Mb is the bending moment, y is the distance from neutral axis to the outermost fiber, and I means the mass moment of inertia. Again for rectangular section I is equal to bd cube by 12. For circular section I is equal to pi by 64 into d raised to 4. That means depends on different section we can take the value of I, we can substitute, you will get the bending stress induced in the component because of this bending moment mb. If shape is irregular other than circular, rectangular or square, for a irregular cross section the parallel axis theorem which is used to find out the I value of I, try to understand, and you might have studied in applied mechanics this parallel axis theorem to find out the I for the the element having a irregular cross section. Then another indirect stress that is due to the torsional moment. When you will find the transmission shafts are subjected to external torque. Look at this. This T is the external torque, or you can say instead in figure is T is shown, but I am going to use the MT is for twisting moment. That it should be MT here. This torque or the shaft when subjected to twisting moment MT. So what is going to happen because of that internal stresses which are induced to resist the action of twist, and these internal resisting the stresses are known as the torsional shear stresses. And these torsional shear stresses are determined by using again this simple equation tau is equal to mtr by j. Mt is the twisting moment, then r is the distance from this neutral axis or radius, you can consider that d by 2. J is the polar moment of inertia, and generally you will find the shafts or transmission shafts are having circular cross section. The polar moment of inertia is equal to pi by 32 into d raised to 4. You can substitute here all these values, you will get the tau is equal to. Again second thing what is happening here, the stresses, these stresses or distribution of torsional stresses will find maximum at the outer fiber and zero at the axis of rotation. And important thing, the angle of twist, that is important because of this twisting or the torsional moment. You will find there is, you will get the angle of twist, that theta, always you have to check it in design and of transmission shafts or the elements which transmit some the torque or the power. So how to find out this, the angle of twist, and which is given, that is g theta is equal to mtl by j into g. Mt is the torsional moment, L is the length of shaft, G is the polar moment of inertia, and G already we know that the G and theta r means theta is in radian. Again to convert theta it into radian, so what we have to do, convert it into angle. The multiplied this term by 180 by pi, therefore theta in degree is equal to 180 by pi into mtl by into j into g. Again what we have to do, but j is equal polar moment of inertia for circular crossing pi by 32 into d raised to 4. We are going to substitute, and at the end you will get theta is equal to 584 mtl upon g into d raised to 4. By using this expression we can find out the theta, that is angle of twist. And angle of this, how much is the permissible limit of angle of twist, depends on the type of shafts, whether the line shafts, whether the spindle shaft, and based on that when this angle of theta is within the permissible limit, we can say our design is safe for the shaft. This is about the torsional moment. Then again you will find in design of the shaft is subjected when the component which is mounted on the shaft such as gears, sprockets or pulleys, there may be possibility of bending of the shaft and it transmits some torque or power, and because of that it is subjected to torsional moment. That means shaft is subjected to the third classification, combination of the stresses. That means shaft is subjected to combined bending moment as well as the torsional moment. And that time we are going to use the equivalent twisting moment, equivalent bending moment, and by using theories of failure we are going to find out the dimensions of the shafts. Try to understand. Then next one, another terms or the stress which is associated with the machine in design, that is bearing pressure. Bearing pressure is also a localized compressive stress. you will find at the area of contact between the two components. But when to say this compressive stress is a bearing pressure, when there is a relative motion between the two components. Look at this. This is the pin and this is the bracket here you will find. And when we are going to, if there is a relative motion between this pin and this bracket, you can say the bearing pressure gets induced in it. Bearing pressure means compressive stress. The localized compressive stress at the area of contact between two components having relative motion between them, relative motion between this pin and this bracket. Then and then you can say this compressive stress is a bearing pressure. But how to find out it? The bearing pressure is equal to again force upon area. But which area? Again, when it is, if load is acting on it, you will find here the projected area that we have to consider this L and diameter of the pin D. The area is equal to L into D. Therefore, bearing pressure is equal to force upon projected area, that is L into D. Example, bush and pin, where you will find the bearing pressure, because if two components having relative motion, then and then this compressive stress is known as bearing pressure. Then another term, that is crushing stress or bearing stress. When to say, now take the same example, but when there is this pin and this bracket doesn't have no relative motion between them, they are properly fitted, and then the induced stress here is a compressive stress. But this compressive stress between these two components having no relative motion is known as crushing stress or bearing stress. And again, how to find out this? For that purpose, again we are going to use bearing pressure or crushing stress is equal to force upon projected area. Again, we have to consider the which part of the pin which comes in contact this bracket, and accordingly we are going to take this projected area. Again, this is L, again this is D, the projected area L into D. The bearing pressure is equal to F into L in D. You will find such examples in rivet, nuts, bolts, key and shafts. This is about the different stresses induced in the machine component. Now let us see. Sometimes in actual practice, while for simple elements, we have seen that the line of action of the forces passes through the centroid of the cross section, and accordingly we have taken the we have used the different relations of stresses induced in the component. But in actual practice, in some of the mechanical applications, some of the mechanical components are subjected to eccentric load. Eccentric load means the line of action of that load which does not pass through the centroid of the axis. Look at this. This is the machine member which is subjected to load, but the line of action, this is the centroidal line or line of action of this force P, it does not pass through this centroidal line or axis. Then and then we can say the load which is acting at some distance from the centroid is known as eccentricity, or you can say it's a eccentric load. Try to understand. And you will find in many applications such a situation arises, and to design such a mechanical components we have to use the case of components subjected to eccentric load. Now how to design it? You will get the situation. Now the load which is which does not, this load P is P which is not passing through the centroid of the cross section. Try to understand. It is at a distance of A. So how to solve this problem? So for that purpose we have to use the principle of statics. According to this principle of static, this eccentric force P can be replaced. How to replace? So first of all, we have to, this parallel force we have to pass through the centroidal axis. This is one. So by replacing force at a distance of P, we are going to locate its position, that force passing through the centroidal axis. Look at this another. I have shown this force at the centroidal axis, and the couple, along with this couple, P is going to act. This P into E, this couple which is going to act. So this diagram or figure which is equivalent to this one, that means this eccentric load condition we have prepared in this way by using principle of static. That means the parallel forces passing through the centroid along with this couple P into E. And then what we have to do, because of this force P which is passing through the centroidal axis, so because of that direct stresses are going to induce in it because of this force. Now suppose it's a tensile force, so you will get the tensile stresses which are going to induce in it, and these tensile stresses are calculated sigma T is equal to P upon area. And because of this couple, again here the bending stresses are going to induce in it. These stresses are also we have to find out. Now look at this. So that's why I have separately constructed this diagram. Now here this P line of action is not passing through the centroidal, which is equivalent by using the statics, the principle of static. We have shown the line of action of the P through the G plus along with the couple P into E here this. Because of this force, the stresses are going to induce, that is direct tensile stress or the compressive, depends on this force. Now here in this situation you will get P by area, that is sigma T, and because of this couple again stresses are going to induce, that we have to determine. And again here is the addition along with this couple, that's why we have to superimpose these stresses, direct stress plus the stresses induced because of this couple P into E, and then equating with the permissible stresses we can find out the dimensions of the component. Look at this here, because of this direct stresses you will get the sigma T is equal to P by A, and because of the couple you will get MBY by I. MB means bending moment, or here it is P into E, MBY by I means mass moment of inertia. You can substitute here all these values, depends on the cross section. Again what you will get the stresses, you have to superimpose. Sometimes depends on the direct tensile axial load or compressive load, so you will get sigma is equal to P by A plus minus PEY by I, and PE is nothing but MB into Y by I. In this way, by superimposing the direct stresses and the bending stresses, we can solve the problem of components subjected to eccentric load. Try to understand. Thank you. I have reported B. Bandari's book, Design of Machine Element, 3rd edition, McGraw-Hill publication. If you have any query, you please contact me at 9890426679 or mail me at pbkushari@kkwork.edu.in.